Welcome back to the deep dive. Today, we're plunging into, well, a really fascinating corner of the OEIS, the Online Encyclopedia of Integer Sequences. This one's especially for you number theory students out there, particularly if you're grappling with combinatorics. We're tackling OEIS A000334 today. It's all about four-dimensional partitions. Our goal, to unpack what these actually are, how they work, and, why mathematicians find them so compelling.
Yeah, that's a great example. This sequence, maintained by the OEIS Foundation, originally put together by Neil Sloan himself, it really represents a rich area of study. You look at it and think it's just numbers, but there's so much depth in combinatorics there.
Okay, let's jump right in then. Number of four-dimensional partitions of n. That phrase itself, it sounds pretty abstract. Before we even get to the four-dimensional part, maybe a super quick refresher. What's a basic integer partition?
Absolutely. Good idea. Before we add dimensions, let's ground ourselves. So an integer partition of some number n is just, well, a way of writing n as a sum of positive integers. The key is the order doesn't matter. Like for the number 3, you can write it as 3, or 2 plus 1, or 1 plus 1 plus 1. Those are its partitions. Now, A000334 counts these, but in 4 dimensions. You might sometimes see older references, too, like M3858 or N3580.
Got it. So sums, but with layers.
Mm-hmm.
And the sequence itself, A000334, looking at the first few terms, wow, for n equals 1 through 10, it goes 1, 5, 15, 45, 120, 326, 835, 2145, 5345, 132, 20. I mean, those numbers just explode. That complexity ramps up incredibly fast. Right, so four-dimensional still feels tricky to visualize with numbers. Is there a more intuitive way to think about what that structure means?
There is, thankfully. Gus Wiseman, in the OEIS entry, gives a really helpful description. He calls them chains of chains of chains of integer partitions. Think of it step by step. A 1D partition is just that sum we talked about. For 2D, you take that list of numbers in the sum and you partition that list. For 3D, you do it again to the result. So for 4D, we're nesting that process 4 times. It's less about physical space, more about layers of combinatorial structure, kind of like a numerical fractal in a way.
Okay. Chains of chains of chains. That helps. Like levels.
Exactly. Let's try a couple of tiny examples. For n1, the sequence value a1 is 1. The only partition is just 4 levels of nesting.
Simple enough.
Right. Now for n2, a2 is 5. So you get things like 102, that's 1. Another is a11. That structure means a partition of 1 and another partition of 1 at the deepest level. And when you get to N3, where A3 is 15, it gets even more involved. You might see structures like 1, 1 on 1, or maybe 1. The point isn't to list them all here.
Right.
But see that nested, almost Russian doll-like structure with sums inside.
That iterative picture makes a huge difference. Okay, I can sort of picture the layering now. So beyond the, let's say, combinatorial puzzle of it all, why the intense focus? Why do mathematicians study these really intricate things? What's the bigger picture?
Well, connecting it out, what's really striking is that these highly abstract things, these 4D partitions, they aren't just mathematical oddities. They're part of some serious research. Neil Sloan included this sequence way back in his original Handbook of Integer Sequences in '73, and then again in the Big Encyclopedia in '95.
So it has history.
Definitely. And even earlier, you had folks like Atkin, Bratley, McDonald, and McKay doing computations on m-dimensional partitions back in 1967. This isn't new territory, but here's where it gets really interesting for me. More recent work, like a 2011 paper by Balakrishnan, Govindarajan, and Prabhakar on the asymptotics, how these grow for large, and also a thesis by Naveen from the same year, they actually connect these concepts to statistical mechanics.
Statistical mechanics in physics, that seems like a huge leap.
It does, doesn't it? But yeah, specifically in areas like condensed matter physics, it seems these combinatorial structures can model something about particle arrangements or energy states in complex systems.
Wow. So a sequence that starts with counting sums ends up potentially describing physics? That's incredible. And you mentioned undimensional partitions earlier. So A000334 isn't alone, right? It fits into a broader pattern.
Exactly. It's part of a whole family. The OEIS cross-references it with sequences like A000219, that's for 2-dimensional partitions, A000293 for 3-dimensional, A000390 for 5-dimensional, and so on. It shows there's a consistent mathematical framework here for thinking about these higher dimensional ways of counting. It's quite elegant, really.
So this journey into just one OEIS sequence, A000334, really shows how a list of integers can unlock these incredibly complex mathematical worlds, and then unexpectedly, those worlds connect back to other fields like physics. It's quite something. So maybe a final thought for everyone listening. Consider how this idea of dimension applied to partitions kind of challenges our basic notion of counting. It really pushes us to think about what numbers can represent. I definitely encourage you to browse the OEIS. Who knows what other fascinating stories are hidden in those sequences.